All right, so let's start by importing TensorFlow. So import TensorFlow as TF. And inside TensorFlow, there is the Keras. And because I'm copying the code from two different sources, I ended up using both keywords, so I'm going to import them separately. I could have just said tf.keras instead of Keras, but I'm just importing it separately. And then we'll have the usual NumPy and matplotlib. And then we are also going to use the MNIST data set. So let me do import TensorFlow data sets as TensorFlow data sets. Okay, TFDS. Okay, let's execute this. It will take some time. Importing everything. Okay, so that's done. Now we are going to define the MNIST training and test sets. So let's say MNIST is equal to TF dot Keras. I just realized something. Okay, datasets dot MNIST. Yeah, there's another code that uses TFDS, but yeah, I had to go through several different versions of such a code to find the one I wanted. So I imported the data sets as TFDS, but I ended up not using it. So I'm just doing xtrain and ytrain, comma, xtest, ytest as MNIST.load data parenthesis. Okay, so let's shift enter. It's going to download everything, and because I already tried this last night, the download is pretty quick. It's already on my local drive, but if you're following this, it might take a little bit more. Okay, so let's see what the training sets look like. So xtrain.shape, and this is basically 60,000 bitmap images. That's 28 by 28. You could also do, let's see, xtest.shape. Yeah, so I guess in total there's the data set is 70,000, and it's already divided into train and test for us. So we'll be using 60,000 images to train it, and then 10,000 will be used to test it. Okay, just to see what's in there, let's just look at xtrain, and let's look at the very first thing that's in xtrain. What's the first image? Okay, what does this look like?
Number 5.
5, right? So ytrain 0 better be 5 as well. Yeah, so that's right. And you can look at the next ones, like change this to 1. Next one's 0, so the next one should be 0 as well. Okay, so it's annotated correctly. Now we're going to do a few things. For example, for the neural networks it's good to have all the numbers between 0 to 1. So I'm going to reformat the xtrain and xtest. So xtrain will be xtrain. First, change the type into float 32 and divide it by 255 dot. Okay. Now, float 32 means it's using 4 bytes to represent a decimal value, and that's called a single precision. A lot of the computer calculations are done using float 64, which is using 8 bytes. Those are called double precision. And float 32 will make the format of the things in xtrain as something that's smaller in memory footprint. And also, most GPUs have faster processing time for single precision than double precision. So that's why rather than just saying xtrain divided by 255, we're doing xtrain as type float 32 and divide by 255. Now, why 255? Well, that's because a bitmap grayscale goes from 0 through 255. So the highest value, 255, which is a white pixel, is going to be converted into 1, and all the other values will be values between 0 and 1. Okay? So we do that, and then we're going to do the same thing for the X test. So let me just copy this thing. Put this as test, and do the exact same thing. Okay, another thing is, oh, I forgot to explain to you this other cross entropy when you have more than one output. Yeah. Okay. So what I need to do is I also need to change the Y train and Y test as a one hot encoding vector. You know what one hot encoding vector is, right? No? So for example, 0 would be converted into 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And 1 will be converted into 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. And then so on and so on. Okay, so in other words, numbers 0, 1, 2, 3 until 9 are converted into a vector of length 10, where most of the entries are 0 except for 1, which is 1. Okay, that's called one-hot encoding. It's a nice way to change a categorical data into a vector. Well, today, in our case, we do have a numerical value, but we're really trying to classify, so it's easier for the neural network to decide if it's a one-hot encoding one. Okay, so we're going to do tf.one-hot encoding, one-hot, and Y train, and then as type. I'm actually not so sure why I need the as type, but yeah, np.int32, comma, depth equals to 10. Okay, and then we have to do the same thing for the test, so let me copy this. And change this to test. And shift enter. Okay. So now let's see print Y train. Let's see what's in the number 2. Okay. And plt.imshow x train 0. Okay, let's see. So this looks like 5 again. Oh, sorry, this is 0. Okay, this is a 4. And as you can see, 4 is correctly encoded as a one-hot vector as this one will be 0, 1, 2, 3, 4. So this is the place where it should be the one for 4, and it correctly gives you a 1, right? Okay, so that's what we have.
For a second,
Yes?
I'm getting an error for my test, for white underscore test.
Uh, Figured it out? Okay. All right, so now let's actually build the model. Okay, so here we start building the model. Model is going to be Keras.sequential. Now Keras gives you, allows you two kinds of models. There's the functional and the sequential. The simpler ones are always sequential, but then say if you have a mix of two different kinds of machine learning models where it takes data in two different ways and at the end you have to merge it somehow, those kind of things will need something called functional. Okay, but sequential is very simple. It's just you just build layer by layer. So we're just going to add layers to this. Now what we want to do first is to add the flattening layer. So I'm going to do model.add keras.layers.flatten. And when you draw the schematic picture of the machine learning model that we use, this flattened model is really not needed, but the problem is that we have a two-dimensional array, right? And when you build Keras layers, it's very sensitive to the shape of the input. So if you have the wrong shape of the input, it complains. So you have to first flatten the 28 by 28 into a single array of 784. 28 times 28 is 784. And that's what we want. Okay, so input shape is 28 by 28. And that's going to get flattened into 784 single dimensional array. Okay, so that's what I'm going to add, and then I'm going to add the next one. Let's copy the above actually. Instead of the flatten, now we're going to put a dense layer. And then you have to tell it how many nodes should be in this dense layer. And this dense layer, you want it to be, this is when you start tweaking. You don't exactly know how many dense layers you would want. Definitely more than 10, because that's what it is sent outside. The dense layer, I have it in my example code as 128, so I'll just use that one. Now we're going to use the activation function as RELU. And you could also use sigmoid instead, but sigmoid is going to run slower because calculating the derivative is slightly harder with the sigmoid. Yeah. And then let's copy this again. And the next layer is going to give you 10 outputs, one for each output. So one node is responsible for giving you the probability that this image could be a 0. The next node will tell you if this image is a 1 or not. And for that, we're going to use a special kind of activation function called softmax. Okay. Yeah, and once the softmax is sent out, it gives you the probabilities for each one of them, and then we will have model that dot compile, and optimizer. We want to use Atom, and then loss function will be categorical cross entropy, and then metrics equals to accuracy. Okay, so let's do this. Oh, sorry, input shape should be equal. Right. Sorry about that. What's wrong? Oh, activation function is spelled wrong. Activation. Huh? Oh, activation, not activation function. Right. Okay, good. So that's done. All right, let me try to explain a little bit what's going on. Here's what we just built. So here's an image, 28 by 28. That gets flattened so that it's like, and total length of this will be 784, which is 28 by 28, okay? And all of these inputs are some values between 0 and 1. Those get in here. And then what happens is you have this hidden layer, and these are 128 nodes. And because it's a dense layer, what happens is that every input gets sent into the next layer. So it's like here, 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 here. Okay? And then the next one has, that's what you have. So one nice exercise is to think about how many parameters are in each of the nodes. So in here, of course, the next one is your, so if I say phi is the ReLU function, how is this output computed? It will be phi of input x1 times the weight 1, right? Times plus weight 2 times x2, all the way up till, what's the last number? 784. Weight 784 plus the last number should be, huh? B1, what's that? What's that called? Bias. No, well, it's also called weight. It's part of weight, but this one's called, these are weights and this is bias, but just for convenience, people just call every one of these as weights as well. All right, so these are all parameters. Okay, so here are weights, 784 weights, and 1 bias. So you have a total of 785 parameters just for this one single node. But then you have how many of them? 128 of them. So you have 128 times 785 number of parameters that control this layer. It's a huge model already, right? And then you have the next node, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you have 10 outputs, and the first one will be for 0, and the next one will be 1, just like that, okay? And then this is sent by the softmax function. So that's the one that I have to explain to you what happens there. And then the final loss function is computed like this. If I say A1 is the input from here, so if I say this is A1, A2, let's say A0, okay? A1 way up till A9, then what you do is you have either so there's the actual value of y, right? So the categorical loss function does this. Negative is y equals to 0, so that's like a true or false, 1 or 0 type thing, times log of A0. Okay? Plus is y equals to 1 times log of A1. All the way up till
A9.
y equals to 9 times log of A9. That's what it does. So that what you want is the one that is correctly represented should give you something close to 1 for this to be minimized. And this summation is because you have to add everything with the batch. So if your batch size is, say, 64, then you're adding 64 of these inputs, and you have the summation, and that value has to be minimized somehow. Okay? So that's what it does. Now, this categorical cross entropy only makes sense if these are probabilities, because it comes from the probability distribution, probability theory. And so what you want is, you want to have these outputs to be values between 0 and 1. Probably these are values between 0 and 1. And you also want their sums to be 1. Okay? So how do you make it happen? Because probably the values that come in here will be, we don't know what's going to come to this node. So how do you enforce them to give you that output? And that's the softmax. And the way you do it is, let's say you have, so let's say Z0 is the value you receive, and you compute this, something like this one. So that's your Z0, okay? So some weights times the inputs from every area, so you get some Z0. And the way you get AIs will be AI is exponential function, or E of negative ZI, over summation of all the E to the negative Z case. You're adding over case. So what it does is it just calculates this, and because exponential functions are always positive, this will always be bigger than 0. And if you just have like 3 values, what happens? It's like e to the negative z1 over e to the negative z1 plus e to the negative z2 plus e to the negative z3. So that will be output of one node, and the next node will be this replaced by 2. The next one will be 3. So if you add them up, the denominators are the same, and the numerators and the denominators are the same, so you end up with a 1. So you can easily see that. And this kind of idea comes from statistical physics. And it just enforces everything to be values between 0 and 1, so that this last layer makes sense. Okay? So that's what we have. Right. So now let's see how it, yes, you have a question?
Yeah, how you know the next node should be 128 from...
Oh, we don't know. We don't know if this should be 128. You could increase this or shrink this. And it's just, those are called hyperparameters. It's like, it's not part of the parameter, but it's something that you have to tweak. So in practice, machine learning is a lot of tweaking this or that. You just like try to change the structure of the layer. You try to change the number of nodes. There's so many things that you can start changing, and those are hard to do. Okay. All right. So that's what we have. Let's just look at the model summary. And you'll see that this number of parameters is really 120 times 785, just like what I wrote on the board. And so these number of parameters can be calculated using the similar thing. See, 129 times 10 is 1290, right? Okay, so now we have to...
Summary,
summary gives you how the structure.
Oh.
This. Oh yeah, model.summary. Yeah. Okay, now let's actually train it. That's model.fit. And we feed in X train, Y train, and then batch size. Batch size, I found it to be, the batch size really depends on your GPU. Some GPUs are powerful enough that it can take a lot of batch size. Some GPUs are small and you have to shrink the batch size. I just went with 2048, but you should just try this and that. Now what happened? Epochs. Okay, so accuracy goes like 70%, 88%, 95, 96. Yeah. If you ran this on your own computer without a GPU, this takes a long time. So accuracy goes way up till 40 epochs, 43. Yeah. Okay. If you're wondering why it ends at 30, see, we have 60,000 examples in our training set, right? And our batch size is 2048. If you divide, you get this much, so that's why it goes 30. If I reduce the batch size to something smaller, then this number will increase. But each epoch is when, one epoch is when all the data set from the training set is seen once. It's processed once. That's one epoch. Okay, now let's see. Let's now do the prediction. Y prediction is model.predict X test. Will predict. Now we have to convert this. Y predict classes equals to np.argmax of y predict axis equals to 1. So I have to convert the one hot vector into actual values to feed into some other things. So let me do that for the y true as well. Y true is same thing, np argmax, but this time we put in y test. Okay. So we've managed to go back to the what was before the one hot encoding. Now let's use the sklearn, import confusion matrix. I forgot that Colab doesn't allow tab completion. Too bad. And then if I do confusion matrix, y true, comma y predict classes. What happened? I don't know what happened. Oh, I made a Y capsule. Sorry. Okay, so if I do that, that's what I get. Beautiful, right? And then I can do from sklearn.metrics import classification report, print classification report of these things, right? So copy that. put it right here. Shift enter. Now, what's going on? Oh, sklearn. I guess I'm running out of time, that's why. Okay, so great, right? So very good result. Now I still want to show you just one more thing, okay? So import OS, no. I have to, from google.colab, import drive drive.mount, content drive. So I want to connect, because I have some numbers, PIL, import image. And we're just going to load up. So this one you won't be able to do because you don't have the files ready, but I'm just showing you. So if you have, great. So I have 4. And here's the important part. If you want to process your own thing, you need to reshape. So the thing is 4, if you 4 equals to numpy.array of 4, and then you have to reshape it so that it's 1 comma 28 comma 28, because it's like a data set with just one entry. That's what it is. Okay, and then if you do model.predict 4, that's harder. So let's do argmax. So np.argmax model.predict.4, and then axis equals to 1. Yep, got it. That's all. Yeah.